Section 11.1 Parametric Functions. Parametric differentiable formulas. If x and y are both differentiable functions of t, and if dx dt does not equal 0, then the first derivative is dy over dt over dx over dt. Now we're going to work with functions where x is defined by t and y is defined by t. And to find the derivative, we take the derivative of y over the derivative of x. If y prime equals dy dx is also a differentiable function of t, then the second derivative is the derivative of the first derivative, but there's a little catch. We have to divide by dx dt. So there's a little extra step. Example 2, analyzing a parametric curve. Consider the curve defined parametrically by x equals t squared minus 5 and y equals 2 sine of t for 0 to pi. A. Sketch a graph of the curve in the viewing window -7 to 7 by -4 to 4. Indicate the direction in which it is traced. So we're going to put the mode of our calculator into parametric. We'll go to y equals, and we have x1 is t squared minus 5, and y1 is 2 sine of t. And let's go to the window, not zoom, window, and we're going to go from 0 to pi with the t, 0 to pi with the t, and then x is going to be -7 to 7, and y is going to be -4 to 4. So let's graph this, and we can see that the graph is going from -5 to approximately 5. So here's A, here's the little sketch. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And the graph is crossing the y-axis somewhere between 1 and 2. So maybe we're doing something like that right there. And then it says indicate the direction in which it is traced. So the graph went from left to right. Letter B, find the highest point on the curve, justify your answer. Well, x dictates whether we go left or right, and y is the up or down. So we want dy dt. We want to take the derivative of y, which is 2 cosine of t, and we want to set that equal to 0. So equal to 0, well, cosine is 0 at pi over 2. So we look at, we put pi over 2, we put this on the number line, and we can go, well, we need something before pi over 2, which is pi over 4. And the cosine of pi over 4 is positive square root of 2 over 2. And then how about 3 pi over 4? And that's going to be negative. So the first derivative of y changes from positive to negative over pi over 2, but they want the point. So we plug pi over 2 in for x, and that's going to be pi squared over 4 minus 5. And 2 sine of pi over 2 is 2. Now to justify this, dy dt changes from positive to negative, so that must be its maximum or its highest point. Letter C, find all points of inflection on the curve. We need dy dx. We need the first derivative, which is the derivative of y, 2 cosine of t over the derivative of x, which is 2t. Now we can cancel out the 2's, so we get cosine of t over t. Now we have to take the derivative of this. So d2y over dx squared is equal to bottom times the derivative of the top minus the top times the derivative of the bottom, which is 1, and that's going to be over t squared. But then we have to divide this by the derivative of x. So the derivative of x is 2t. So we're dividing this by 2t. Well, that's a complex fraction. So we're going to multiply the top and bottom by t squared, which is negative t sine of t minus cosine of t over 2t to the third. Well, we can't have a point of inflection at an endpoint. So the 0 that makes the second derivative undefined, we're not going to consider that because it is an endpoint. Well, now we want to know where the top is equal to 0. So let's go to mode. we'll go to function. We go to y equals, and we already have that in there. So negative t sine t minus cosine of t. We want to know where this is 0 from 0 to pi. So we're only going from 0 to pi. Let's graph this, and we'll see where this graph crosses the x-axis. Well, it crosses the x-axis between 2 and 3, so let's go calculate. Let's try that again. Calculate. Yeah, try it one more time. Calculate a 0 number 2, and we're between 2 and 3, and I'll guess 2.7. So the actual value is 2.798. So t equals 2.798, but they want to find all points of inflection. So we have to plug this into x and plug this into y. So let's get out of this. Let's go, we can do x squared and then minus 5, because that x value is still sitting in x. And we get 2.831. So 2.831 for the x. And then we need 2 sine of x for the y, 0.673. 0.673. And how do we know that this is a point of inflection? Because d2y over dx2 changes signs. That's how we know. That's how we justify. Arc length of a parametrized curve. Let L be the length of a parametric curve that is traversed exactly once as t increases from t1 to t2. If dx dt and dy dt are continuous functions of t, then the length is the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. Now this is going to be it's really the Pythagorean theorem. Example 3, measuring a parametric curve. Find the length of the asteroid, where x is cosine to the third, y is sine to the third, and we're going from 0 to 2 pi. Let's go back to the calculator. Let's put this in parametric mode. So we have parametric. Let's go to y1. We're going to put in y, actually in x, we're going to put cosine x to the third. And then in y1, we're going to put sine to the third. So we have sine x to the third. But we're only going to go from 0 to pi divided by 2. And when we graph this, well, the window's kind of messed up a little bit. Let's fix the window. We're going to go from -2 to 2, and we're going to go from -2 to 2, and we'll have a better window here. And notice that only 1/4 of the figure is drawn going from 0 to pi over 2. So to find the length, we're going to take 4 times the integral from 0 to pi over 2 of the square root of, I need the derivative of x squared. So derivative of x squared is equal to, well, the derivative is 3 cosine squared of t, but then times negative sine of t using the chain rule, and then we're going to square that, which is 9 cosine to the 4th t sine squared t. So there's the derivative of x squared. So we have 9 cosine to the 4th t sine squared t, and then the derivative of y is 3 sine squared t times cosine of t, but we're going to square that. So we're squaring the derivative, which is equal to 9 sine to the 4th t cosine squared t. So now this is going to be, kind of ran out of room, plus is under the square root still, plus 9 sine to the 4th t cosine squared t. Now it's hard to see because I kind of ran out of room here, but I can factor out a sine squared out of both and a cosine squared out of both, and I can factor a 9 out of there. So let's go down here where we have some room. We have 4 integral from 0 to pi over 2 of the square root of, I can factor a 9 out, I can factor a sine squared out, and I can factor a cosine squared out. And what's left out of here is, let's see, I factor the sine, cosine squared. And what's left out of this one right here is just sine squared t. Well, cosine squared t plus sine squared t, that's 1. Well, now we have perfect squares left over, and we can take the square root of those perfect squares. Now we're going from 0 to pi over 2 of 3, really absolute value of sine of t, cosine of t. But we're only integrating from 0 to pi over 2, and both sine of t and cosine of t are positive there, so we really don't have to worry too much about that absolute value. Well, let's pull the 3 out. We got 12, 0 to pi over 2 of sine of t, cosine of t dt. And we're going to use u substitution to integrate this. Let u equal, how about sine of t? And du is equal to cosine of t dt. So this becomes 12 integral. Let's change the u. Let's change 2 u's. Let's plug the 0 in for t. Sine of 0 is 0. And then let's plug the pi over 2 in. Sine of pi over 2 is 1. So now we're only integrating from 0 to 1 of u du. We have 12 integral of 1/2 u squared from 0 to 1. Well, that's just going to be half of 12. The answer is 6. Example, x equals t squared plus 2t, y equals t squared minus 2t plus 3, and we're not integrating, but we're doing the problem from -2 to 3. Sketch the parametric equation and include direction. Find the furthest left point. Find where x is a minimum, in other words. So we're gonna do the integers for t, -2, -1, 0, 1, 2, 3. We'll find the x's, we'll find the y's. Well, we need to plug -2 in for the t's up here. We get 4 minus 4, that's going to give us 0. And then plugging -2 in there, we get 4 plus 4 is 8, plus 3 is 11. And doing the same thing except with -1, we get -1, 6. Then we get 0, 3, then 3, 2, 8, 3, and finally 15, 6. So 0, 11 is a little off the map. -1, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3. 8, 3. 2, 3, 4, 5, 6, 7, 8. 3. And then we're off to 15, 6. So it's a graph like that. Come down here. Did I miss one? Yeah, 3, 2. 1, 2, 3, 2 right there. So it dips down, then it comes back up. And here's the direction that it was graphed. All right, so we got the first part, and let's find the furthest left point. Well, that's the x. We want dx dt. The x dictates left and right. 2t plus 2, we want to set that equal to 0. So -2 equals 2t, t equals -1. So this graph is farthest to the left when t is -1. We've already found the point, so the point is -1, 6 is the point that is farthest to the left. Given x equals 4 cosine t, y equals 3 sine t, write an equation of the tangent line to the curve at the point when t equals 3 pi over 4. Well, if we're going to write the equation of a tangent line, we need a point and we need its slope. So let's plug 3 pi over 4 in for x. So we get 4 times negative square root of 2 over 2, which is -2 square root of 2. That's the x. Now let's plug 3 pi over 4 in for the t and the y, and we get 3 times the square root of 2 over 2, which there's not much we can really do with that. Well, now we need the derivative. We need dy over dx. So the derivative of y is 3 cosine of t, and the derivative of x is -4 sine of t. Well, the cosine, we're going to evaluate this when t equals 3 pi over 4, so we get 3 square root of 2 over 2, actually negative, over -4 square root of 2 over 2, which ends up just being 3/4. So there's the slope, 3/4, and the equation is y minus 3 square root of 2 over 2 equals 3/4 times x plus 2 square root of 2. In exercises 23 to 26, find the points at which the tangent line to the curve is horizontal and b vertical. So let's find the derivative first. dy dx equals 3 cosine of t over the derivative of x is -3 sine of t. We can cancel out the 3's, and it's negative cosine of t over sine of t. So for letter A, we want to know where the tangent lines are horizontal. That's when the derivative is 0. So we want to know where negative cosine of t is equal to 0. And we'll just go one trip around. We'll just go from 0 to 2 pi, and cosine is 0 at pi over 2 and 3 pi over 2. And for b, we want to know where sine of t is equal to 0, and that's at 0 and pi. Well, let's graph this real quick. Let's make sure we're in parametric mode. We're going to go to y equals. Let's clear the x out. That's negative 2 plus 3 cosine of x, or t in this case. And then y is 1 plus 3 sine of t. And let's make sure we delete. Let's get over to that 3, delete that out. There we go. And let's go, how about zoom? Well, we can do 6, but that's not going to get us. Oh, yeah, it did get us the whole graph because the default is 0 to 2 pi. Well, supposedly, we have horizontal at pi over 2 and 3 pi over 2. Well, that's going to be at the top and the bottom of this ellipse. So let's go second, calculate. How about just a value? And if we plug in pi divided by 2, that's going to put us up at the top where the tangent line is horizontal. And then 3 pi divided by 2, that should put us on the bottom where the tangent line is again horizontal. Well, 0 should give us a vertical tangent line, and pi should also give us a vertical tangent line there over on the left.